All right, this video is going to be about strong acid and strong base titration. Okay, so an acid-base titration in the simplest way is whenever you have a burette and you're titrating a known concentration through the burette into an unknown concentration in a flask. And so you know how much you put into here, and you add an indicator. So you know the volume here. You might not know the concentration, but you know the volume. And you're going to add a known concentration and a known volume of this to this container until a color change occurs. So your indicator changes color at the right time to tell you that the reaction is complete, and then it's your equivalence point or your end point of the titration. The two things are not exactly the same. The end point is when the indicator tells you that it's over, and an equivalence point is when it's completely equal. The reactants are stoichiometrically equal, so their mole-to-mole ratio is equal there. But regardless, your endpoint should come very close to your equivalence point, so you have to pick the right indicator for that to happen. Anyway, so you can calculate your unknown concentration using this method. We've done this in class, and so you should be familiar with this process. All right, so the new type of way to do this is to use a pH probe, and this is the equipment that I have at the school, where we have this thing right here is actually a drop counter, and so the drops drop through that, and they're counted, and as they're added, it's calibrated in a way to where it can convert the drops to volume. So it knows how much volume has been added of whatever is in this. So this is our burette. And then this right here is the pH probe. A pH is taken and plotted, and we get a titration curve from it. So pH and volume is being monitored, and we get a curve from it. Okay, so let's talk about the curve. All right, so for a strong acid, strong base titration curve, it'll look like this. And the equivalence point, which is right here, is right in the middle of that curve. And it's always going to be at pH 7 for a strong acid, strong base. So you can always tell when a strong acid was titrated because the equivalence point is going to be exactly at 7, as long as a strong base was also used. Okay, and your pH is going to start off pretty low. Usually weak acids will start off a little bit higher. We'll talk about those later. So our equivalence point happened at 50 milliliters of base, right? So prior to 50 milliliters of base, the acid was in excess, and after 50 milliliters of base, the base was in excess. So let's look at that closer. Here, from here to here, whatever acid, we'll just say HCl was being used. So we'll say that this will HCl plus NaOH, and that would make NaCl plus H2O, right? And so for strong acid, strong base, this dissociates completely into H plus and Cl. And this will dissociate into sodium and hydroxide because it's strong. And sodium chloride is completely soluble, so we get sodium ions and chloride ions. And then that's water, of course, so it doesn't dissociate. So sodium and chloride are spectator ions, and they cancel out. So really our reaction is H plus OH goes to H2O. And so for right here, the beginning of the titration, hydrogen is in excess. And then after the endpoint, hydroxide is in excess. So in order to find the pH along that line, if you didn't have this curve, you'd have to figure out how much you have of each one of those in excess. All right, so let's do one of those problems. Okay, so we want to find this pH of the solution at each point when 25 milliliters of HCl is titrated with 0.25 molar NaOH. The first point is before we've added any base. Well, that's really easy. So we've got 0.50 molar HCl. So all I need to do is take the negative log of my H concentration, which is going to be 0.5, and so that's going to be 0.3. Okay, so that's the pH before we've added any base. Now the second point, I have to figure out what's in excess, right? And I'm going to use millimoles here. You can use moles if you want to. That means you're going to do a lot of conversions for volume, but it's up to you. So for H, I have 25 milliliters of 0.5 molar. So that means I've got 25 milliliters And to find my moles, I've got 0.5 moles in every liter. So I'm going to take 25 times 0.5, and that's going to give me 12.5 millimoles. Because liters cancels out, and I'm left with millimole of H. And then for OH, I'm using a 0.25 molar solution, and I've added 25 milliliters. So 25 milliliters times 0.25 moles per liter, and that gives me 6.25 millimoles of OH. So that means all of these 6.25 millimoles of OH is going to react. And 6.25 millimoles of H has to react with it, right? Because the mole-to-mole ratio is 1:1 for this. This is the reaction that I wrote down on the previous slide. So we end up with H plus OH goes to H2O, right? So the sodium and the chloride cancel out, and we get that. What I have left over here is I'm going to have 6.25 millimoles of H plus in excess. Now the problem is that I have added this volume to this. So my total new volume is 50 milliliters. I'm going to divide this by 50 milliliters in order to get my new concentration, and the milli in millimole and the milli in milliliter end up canceling out. And I get that my H plus concentration is going to be equal to 0.125. And so now I can find my pH, just take the negative log of 0.125, and I end up getting 0.903. So then at the third point, I need to figure out what's in excess. So I'm going to do the exact same thing. My H plus, well, none of that changed. I started out with 25 milliliters, 0.5 moles per liter. So I have 12.5 millimoles of H plus. And then my OH, this time I'm using 50 milliliters, and the concentration is still 0.25. And so we end up getting, that's 12.5 millimoles of hydroxide. So these both are equal. So this is the equivalence point. And since it's a strong acid, strong base, that means that my pH is going to be at pH 7, because all we have is water. And then my fourth one, I'm going to do over here. I'm going to try to squeeze it over here. All right. My H is still going to be the same. And I get 12.5 millimoles of H. And then my OH, I add 75 milliliters of 0.25, and that gives me 18.75 millimoles of OH. So now I have 6.25 millimoles of OH extra, because when I compare these two numbers, H is going to run out after all of that is used up. And so I have 6.25 millimoles of OH left over. So now I need to find my concentration of OH, and that's going to be equal to 6.25 millimoles of OH divided by my total volume. So my total volume, I have 75 milliliters has been added to 25 milliliters, so that's 100 milliliters. So milli cancels out, and my concentration is 0.0625. So if I take the negative log of that, my POH is 1.20, and so my pH is 12.8. All right, so I know that that's a lot, but we don't have to do any of the weak acid or weak base titration calculations anymore, so this is really easy. So all you have to do is figure out which one you have as an excess, find the new concentration, and find the pH of it. Okay, so this is very similar to what we did at the beginning of the year. You really need to get these down if you didn't get them down then. All right, so we have a lab in which 25 milliliters of a 3 molar H2SO4 is being titrated with a 1.5 molar NaOH. How much NaOH must be added to get to the equivalence point? So you always start with what you have the most of. And so we have more information on H2SO4. So I'm going to start with that. And I always start with what doesn't have a denominator. Remember, molarity is moles per liter. So I'm going to start with 25 milliliters. And I have 3.0 moles of H2SO4 per liter. And then 1 mole of H2SO4 reacts with 2 moles of NaOH. And I went to NaOH because I want to find out information about NaOH. All right, and it says how much NaOH. So we're looking for volume, and we'll just calculate it in milliliters because it didn't specify. So I have moles of NaOH. So now I can use this because this right here is moles per liter of NaOH. So I have 1.5 moles of NaOH per liter. So moles of NaOH cancel with moles of NaOH, moles of H2SO4, moles of H2SO4, liters and liters. This is going to be 100 milliliters. Now I could have guessed that because this is twice as strong as this. So even if the mole-to-mole ratio was 1 to 1, I would need twice as much of this to neutralize that. But in addition, I need 2 extra NaOH for every 1 H2SO4. So it's going to be times twice. So 25 times 2 times 2 is 100. And maybe you'll get to the point where you can see that too. If not, you can always do this. So this is pretty simple to do even without a calculator. 1.5 goes into 3, right? Twice. So it's 25 times 2 times 2. All right, so one last problem. We have found a bottle of HBr in a lab and you're unsure of what the concentration is. To get an accurate reading, you titrate 20 milliliters of acid with KOH. Okay, so we have HBr plus KOH makes KBr plus H2O. Both of these are strong. So we have H plus OH makes H2O. And we're going to start with what we know most about. So we know 30 milliliters of 1.5 molar sodium hydroxide and it says with KOH. So this should be K. My bad. So this is K. Mole of KOH for every 1 mole of HBr. And that'll give us moles of HBr, or millimoles actually. Because we got rid of liters, we get rid of moles here, so we have millimoles left over. So 30 times 1.5 is 45. And then, so now we have millimoles, we can just divide by the milliliters, right? And the milliliters was 20. And so my concentration is 2.25. All right, and then what is the pH of this reaction after the addition of 20 milliliters? So again, I'm going to do the same thing. So if I'm looking for the pH after the addition of something, okay, so I am going to have to find my H and find my OH and find out which one is in excess. So I use 20 milliliters of acid. That comes from right up here. And it's 2.25 moles per liter. So that's 45 millimoles. And then OH is going to be 20 times 1.5, and so that is 30 millimoles of hydroxide. So that means I have 15 millimoles of H plus in excess because 30 is going to react with this. It's both 1 to 1. And I have a total volume of 40 milliliters. So I'm going to divide that by 40 milliliters, and I get 0.375. So then to find the pH, I take the negative log of that, and it ends up being 0.37. So that might seem really low, but if you take the negative log of 2.25, you get negative 0.35. So the pH has come up. If this would have been the pH of the original acid. So it has come up with the addition of hydroxide. So that's it. It'll get really easy once you do a few problems. So hopefully it doesn't get too easy and then you forget how to do it by the time the AP test comes around.